November 12, 1942, Richmond Shipyard No. 2, California. The morning fog hadn't yet burned off San Francisco Bay when 27-year-old Garrie Thompson, an assembly worker earning 95 cents per hour, stared at a problem that had plagued every Liberty ship built in the previous 13 months. Two massive steel deck plates, each weighing several tons, needed to be drawn together perfectly flush before welders could join them. The standard method required 1,200 individual steel clips, temporary fasteners that held the plates in alignment. Each clip had to be manually positioned, each one had to be cut away after welding, and each one represented wasted steel, wasted time, and wasted man-hours. 1,200 clips per ship. Thousands of pounds of scrap metal. Days of additional labor. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Thompson had watched this process repeat itself on 46 ships since the yard opened. He'd seen workers struggle with the clips, seen welders curse when plates shifted out of alignment, seen supervisors calculate the mounting costs. The mathematics were brutal. At current production rates, Kaiser's 4 Richmond yards alone would build over 700 Liberty ships before the war ended. 700 ships times 1,200 clips. 840,000 clips. Millions of pounds of steel that would end up in scrap bins instead of in ships crossing the Atlantic. And somewhere in the North Atlantic, U-boats were sinking Allied merchant vessels faster than American shipyards could replace them. The solution Thompson conceived that morning was so simple it bordered on obvious. He sketched it during his lunch break, refined it that evening, and built a working prototype in the shipyard's machine shop on his own time over the next 3 days. The device looked like a cast-iron femur with a giant bolt running through its central axis. When positioned between 2 deck plates, the bolt could be tightened to draw the plates together with perfect, even pressure. One tool replacing 1,200 clips, one worker operating it instead of a team wrestling with temporary fasteners. The jackbacker, as Thompson's co-workers immediately nicknamed it, eliminated 1,200 clips per ship and cut 5,000 man-hours from each vessel's construction time. 5,000 hours. 208 days. The equivalent of having an extra worker for more than half a year on every single ship. But Thompson wasn't an engineer. He wasn't a naval architect. He wasn't anyone the Maritime Commission would have consulted when designing the Liberty ship program. He was an assembly worker who understood leverage, understood steel, and understood that survival in modern industrial warfare meant building ships faster than the enemy could sink them. And on this particular November morning, as fog rolled across the bay and workers arrived for the day shift, Thompson was about to help prove that sometimes the most critical innovations in history come from the people actually doing the work, not from the ones designing it. The transformation of American shipbuilding didn't begin with Thompson's innovation. It began 18 months earlier, in a context most Americans couldn't fully comprehend because the scale was simply too vast, the timeline too compressed, the stakes too absolute. When the United States entered World War II in December 1941, the American merchant fleet was catastrophically unprepared for the tonnage war that was about to unfold. The fleet averaged over 20 years old. Most vessels could barely manage 10 or 11 knots. More importantly, there simply weren't enough ships, not nearly enough. Britain, already 2 years into the war, was hemorrhaging merchant tonnage to German U-boats at a rate that threatened to starve the island nation into submission. In 1941 alone, U-boats and surface raiders sank over 1,000 Allied merchant vessels. In 1942, the toll would climb to nearly 1,500 ships. Each sinking represented not just lost cargo, but lost capacity to move troops, ammunition, fuel, food, vehicles, and all the materiel required to fight a global industrial war. The mathematics were existential. If German submarines could sink ships faster than Allied shipyards could build replacements, Britain would fall, the Soviet Union would collapse under the weight of German armies it couldn't supply, and the entire Allied war effort would crumble. The United States Maritime Commission, created in 1936 to modernize the merchant marine, understood this calculus with painful clarity. In 1940, even before Pearl Harbor, Britain had contracted for 60 merchant vessels from American shipyards to replace war losses. The British design was straightforward, a simple tramp steamer based on a northeastern marine engineering design from 1939. 441 feet long, 57 feet wide, designed to carry 10,000 deadweight tons of cargo. Nothing fancy, nothing fast. Just a basic cargo box that could haul war material across the Atlantic. The Americans called it the Ocean Class. Then the Maritime Commission made a decision that would transform not just shipbuilding but the entire trajectory of the war. They would mass-produce these vessels on a scale never before attempted in maritime history. Not dozens of ships, not hundreds, thousands. They would build them faster than traditional methods allowed. They would build them cheaper than conventional shipyards thought possible. And they would build them using a labour force that included tens of thousands of workers who had never set foot in a shipyard before, because every able-bodied man with shipbuilding experience was either already working flat out or being drafted into uniform. The design the Maritime Commission settled on, designated EC-2 SC-1, became known as the Liberty ship. The name came from the first vessel, SS Patrick Henry, launched on September 27, 1941, and named after the Revolutionary War patriot who had declared, "Give me liberty, or give me death." Franklin Roosevelt, reviewing the blueprints at the White House, offered his assessment with characteristic bluntness. "I think this ship will do us very well," the President told Maritime Commission Administrator Admiral Emery Land. "She'll carry a good load. She isn't much to look at, though, is she? A real ugly duckling." Roosevelt's aesthetic critique was accurate. The Liberty ship was deliberately, systematically ugly. Every design choice prioritized speed of construction over appearance, cost-effectiveness over sophistication, wartime expedience over peacetime standards. The hull was slab-sided and graceless. The superstructure was boxy and utilitarian. The ship used an ancient triple-expansion steam engine, a technology that dated back to the late 19th century, because modern turbine engines required strategic materials and specialized manufacturing capacity that didn't exist in sufficient quantity. Liberty ships burned oil when available, coal when necessary, and could lumber along at 11 knots in calm seas, slightly less in rough weather. They looked exactly like what they were: maritime workhorses designed to haul cargo across oceans, survive one journey if necessary, and get built fast enough to matter. But the real revolution wasn't in the design. The design was consciously archaic, deliberately simple, intentionally constructed from common materials using widespread manufacturing techniques. The revolution was in how these ships would be built. Traditional shipbuilding, refined over centuries, proceeded from the keel up. A ship was constructed on a sloped surface called a slipway or shipway. Workers laid the keel first, the backbone of the vessel. Then they built upward and outward, adding frame members, attaching plates, installing internal structures, piece by piece, plate by plate, rivet by rivet. One crew worked on one ship in one location, assembling the entire vessel from thousands of individual components. The process required skilled labor, precise measurements, and substantial time. A merchant ship built by traditional methods took 6 to 8 months from keel laying to launch. The Liberty ship program would shatter every assumption underlying that traditional approach. Henry J. Kaiser, an industrialist with no shipbuilding experience, but extensive knowledge of large-scale construction from building the Hoover Dam, Bonneville Dam, and Grand Coulee Dam, proposed a fundamentally different method. Build the ships in modules. Construct major sections, entire bulkheads, complete deck assemblies, massive bow and stern sections, in fabrication shops away from the slipways. Use prefabrication techniques borrowed from automobile manufacturing and building construction. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Then move these massive prefabricated sections to the slipway and assemble them, joining the large modules rather than building from individual pieces. And here was the truly revolutionary part, the decision that would make or break the entire program. Weld the sections together instead of riveting them. Riveting had dominated ship construction for over a century. Rivets were proven technology. Riveters were trained craftsmen. The process was well understood, reliable, and produced ships that could flex and bend without catastrophic failure because riveted joints allowed for slight movement between plates. But riveting was also incredibly labor-intensive, required skilled workers in short supply, and accounted for roughly 1/3 of total labor costs in traditional ship construction. Welding offered transformative advantages. Welded joints could be completed faster than riveted ones. Welding required less skill to learn, meaning workers could be trained in weeks rather than years. Women could weld, and with approximately 12 million American men serving in uniform by 1943, the industrial workforce desperately needed women. Welding saved steel because plates didn't need to overlap the way riveted construction required. Every pound of steel saved was a pound available for weapons, vehicles, or additional ships. And perhaps most critically for the emergency program, welding enabled the modular prefabrication approach that would allow Liberty ships to be constructed at unprecedented speed. The scale of prefabrication Kaiser's yards achieved defied previous shipbuilding practice. Approximately 80% of the steel for a Liberty ship was already assembled into large modules before the keel was laid on the slipway. In massive fabrication shops covering acres of the shipyard, workers constructed entire sections of the ship. Double-bottom assemblies, complete sections of hull weighing up to 45 tons. Stern frame assemblies with the rudder post, propeller shaft, housing, and supporting structure already in place, bow units with the stem piece, and forward hull plates. Complete deck houses, the superstructure cabins and bridge already fitted out with doors, windows, and interior partitions. Bulkheads, the internal walls dividing the ship into compartments, fabricated as single units with all necessary openings and reinforcements. These modules moved through the shipyard on rolling cranes and railroad tracks, a conveyor belt system borrowed directly from automotive assembly lines. Steel plates and shapes entered the yard on the inland side, passing through cutting shops where they were shaped to specification, then moving to fabrication areas where they were joined into progressively larger assemblies. Small pieces became moderate sections became massive modules, and these modules, each weighing many tons, would be hoisted onto the slipway by the largest cranes available. Some jobs requiring 4 cranes, working in coordination to lift a 200-ton deckhouse into position. The welding itself required innovation at every level. In 1941, most American shipyards had never built an all-welded vessel. The technology existed, certainly. Electric arc welding, using a flux-coated electrode, had been available since the 1920s. But applying it to large-scale ship construction at emergency speeds with largely inexperienced workers was unprecedented. The welders used what was called shielded metal arc welding, or SMAW, commonly known as stick welding. An electrode, a metal rod coated with flux, was held in an electrode holder connected to a welding machine. When the welder struck an arc by touching the electrode to the workpiece, electrical current flowing through the circuit created temperatures exceeding 6,000 degrees Fahrenheit, melting both the electrode and the base metal, fusing them together. The flux coating vaporized, creating a protective gas shield and a slag layer that protected the molten weld pool from atmospheric contamination as it cooled. Each Liberty ship required approximately 50 miles of welding. 50 miles. Hundreds of thousands of individual welds, ranging from short tack welds holding components in alignment to continuous seams running for dozens of feet. The sheer volume of welding was staggering, and it all had to be completed by workers who, in many cases, had been housewives, secretaries, or farm laborers just weeks earlier. The Kaiser shipyards developed training programs that could take a complete novice and produce a productive welder in as little as 7 to 10 days for the simplest welding tasks. More complex joints, positions, and techniques required additional training, but the basic skill set could be taught remarkably quickly. This democratization of shipbuilding skills was essential because the labor requirements were enormous. A typical Liberty ship consumed approximately 574,000 man-hours from the beginning of assembly to delivery. That translated to roughly 750 workers on 9-hour shifts for the duration of construction. At peak production in 1943, Kaiser's 7 yards employed nearly 200,000 workers. Across all 18 shipyards building Liberty ships, approximately 1.5 million Americans learned to weld, to fit steel, to operate cranes, to install engines, to wire electrical systems, and to perform the 1,000 other tasks required to construct an ocean-going vessel. The workforce transformation was as revolutionary as the technical innovations. In Richmond, California, the pre-war population was 20,000. By 1943, over 100,000 people lived in the city, most of them shipyard workers who had migrated from across the country. Kaiser built an entire city, Vanport, on Portland's northern edge, with nearly 10,000 housing units accommodating 42,000 residents. The shipyards operated 3 8-hour shifts, 24 hours per day, 7 days per week. Workers flooded into boom towns that lacked adequate housing, schools, shopping, or infrastructure. Kaiser, understanding that worker welfare directly impacted productivity, provided services unprecedented in American industry. Childcare centers, open 24 hours per day, allowed both parents to work shifts. Health clinics, initially established to treat workplace injuries, evolved into comprehensive healthcare systems that would eventually become Kaiser Permanente, one of America's largest health maintenance organizations. The company encouraged shops, cafes, schools, and other services to establish themselves near the yards. Wages were competitive, 95 cents per hour to start, with overtime available and production bonuses, incentivizing speed and quality. The workforce was remarkably diverse for 1940s America. Women comprised up to 10% of workers in some yards, learning skills traditionally reserved for men and proving, much to the surprise of skeptical supervisors, that welding required precision and steady hands more than brute strength. Slender women could fit into tight spaces between plates where larger men couldn't reach. African Americans found opportunities in Kaiser's yards that were closed to them in most other industries, with some payrolls reaching 50% black workers. Kaiser hired on merit, trained from scratch, and promoted based on performance. And critically, Kaiser encouraged workers to innovate, to identify problems, to propose solutions, to improve the process. The Maritime Commission received over 3,000 improvement suggestions from workers during the war, collectively saving $45 million and 31 million labor hours. These weren't minor tweaks. These were substantial innovations that fundamentally improved how ships were built. Workers who understood the actual process, who performed the work daily, who saw inefficiencies and bottlenecks and unnecessary steps, contributed solutions that engineering staffs had missed. This was the context in which Garrie Thompson invented the jackbacker in November 1942. The innovation wasn't isolated. It was part of a culture that recognized problem-solving ability wherever it emerged, that understood survival in industrial warfare required harnessing every available brain, every creative solution, every marginal improvement in efficiency. Thompson's device saved 5,000 man-hours per ship. On 700 Richmond-built Liberty ships that totaled 3.5 million man-hours, the equivalent of having nearly 1,700 additional workers for an entire year, the steel saved from eliminating 1,200 clips per ship totaled thousands of tons across the program, tons that went into additional vessels, tanks, or ammunition instead of scrap bins. But Thompson's contribution was one among thousands. Another Richmond worker developed a prefabrication system for precision-cut plates that formed the foundation for Liberty ship steam engines, cutting installation time by nearly 90%. Workers created improved jigs and fixtures for holding components during welding. They designed better material handling systems. They found ways to weld in difficult positions, to speed up repetitive tasks, to reduce defects, to simplify complex procedures. Each innovation compounded, each improvement built on previous ones, each solution enabled further acceleration. The results were staggering. The first Liberty ships, built in late 1941, required an average of 230 days from keel laying to delivery. By late 1942, average construction time had dropped to 70 days. By 1943, the industry average was 42 days, with Kaiser's yards regularly completing ships in under 30 days. Oregon shipbuilding maintained a pace of 17 days per round, meaning 17 days from laying one keel to laying the next keel on the same slipway. The fastest ships were built as propaganda exercises, demonstrations of American industrial might intended to boost worker morale and send a message to both allies and enemies about the scale of production capability. In September 1942, Oregon Shipbuilding completed the SS Joseph N. Teal in 10 days. In November 1942, Kaiser's Richmond Yard No. 2 assembled the SS Robert E. Peary in 4 days, 15 hours, and 29 minutes, from keel laying to launch. The Peary's record became international news, covered by newspapers from Seattle to Boston to London. American industrial capacity, it seemed, could build ships faster than anyone imagined possible. But these record ships, important as they were for morale, weren't representative of actual production. The Robert E. Peary was launched in under 5 days, but still required several additional days of fitting out work, installing equipment, completing systems, and conducting sea trials before delivery. The record-setting assembly was possible because Kaiser's yard had pre-positioned every component, staged every module, assigned extra workers, and coordinated the effort with military precision. The exercise demonstrated what was theoretically achievable under perfect conditions, with unlimited resources focused on a single ship. Regular production, while less dramatic, was more important. The average construction time of 42 days by 1943 meant shipyards were consistently, reliably, predictably turning out new vessels at a pace that outstripped German sinking rates. In 1943, Allied shipyards delivered more tonnage than U-boats destroyed every single month. The tonnage battle, the race between construction and destruction, tipped decisively in favor of the Allies. By 1944, 3 Liberty ships were being delivered every day, somewhere in America, sliding down slipways from Richmond, Portland, Baltimore, Savannah, Houston, or any of the other yards contributing to the program. The ships carried everything the war required. A single Liberty ship could transport 2,800 jeeps, 440 tanks, or 230 million rounds of rifle ammunition. The cargo holds could accommodate aircraft fuselage sections, locomotives, medical supplies, food, fuel drums, ammunition pallets, vehicles, and essentially any military cargo that needed to cross oceans. On deck, secured with chains and welded brackets, additional vehicles, aircraft, or equipment could ride as deck cargo. The ships were designed as expendable assets, expected to make one crossing to justify their cost, anything beyond that considered a bonus. Ships performed far better than their 5-year design life suggested. These ungainly vessels, built quickly from inexpensive materials, served for decades after the war, plodding across oceans well into the 1960s and 70s. Some were modified for specialized purposes, some were sold to foreign shipping companies, some served in the Korean and Vietnam conflicts, and a handful were even adapted as support ships for the early American space program, serving as recovery vessels for capsule splashdowns. The ugly ducklings that Roosevelt had criticized proved remarkably durable, precisely because their simple design and rugged construction made them easy to maintain and difficult to break. But before any of this longevity could be demonstrated, before the ships could prove their worth in peacetime service, before anyone could celebrate the program's success, the Liberty ship program had to survive a crisis that threatened to destroy public confidence and potentially halt production entirely. The crisis emerged from the very innovation that had made rapid construction possible: welding. The first indications appeared in late 1942, isolated incidents that didn't immediately suggest a systemic problem. A Liberty ship would be loading cargo in port when a crack would appear in the deck, or a vessel would be at sea in moderate weather when a hull plate would suddenly fracture. The cracks typically started at points of stress concentration, corners of hatches, ends of deck structures, locations where loads or stresses changed direction. In riveted construction, such cracks would propagate until they reached a riveted joint, and then stop, because the joint allowed slight movement between plates and interrupted the crack's path. In welded construction, where the entire hull was effectively one continuous sheet of steel, cracks could propagate unimpeded. Small cracks became large cracks became structural failures. In the worst cases, ships broke in half. The SS John P. Gaines split completely and sank on November 24, 1943, taking 10 crew members with her. By late 1943, nearly 1,500 instances of significant brittle fractures had been documented. 12 Liberty ships, including 3 broken completely in half without warning, were total losses. The timing couldn't have been worse. By late 1943, the program was hitting peak production rates. Public confidence in the industrial mobilization was high. Kaiser had become a folk hero, his name synonymous with American can-do spirit and industrial prowess, and suddenly, ships were cracking, breaking, and in some cases killing crew members. Suspicion immediately fell on the welding. Critics who had always doubted the wisdom of abandoning proven riveting techniques pointed to the failures as evidence that shortcuts and haste had compromised safety. Some blamed the inexperienced workers, suggesting that inadequately trained welders were producing defective joints. Others blamed the emergency production schedule, arguing that building ships in 30 or 40 days created quality control problems. The Navy and Maritime Commission launched investigations. Shipyards faced intense scrutiny. The program that had seemed invincible suddenly looked fragile. If the fundamental construction method was flawed, if welded ships couldn't survive Atlantic weather or normal operational stresses, then the entire emergency shipbuilding program might need to be redesigned, delayed, or abandoned. The strategic implications were grave. If Liberty ship production slowed or stopped, the tonnage balance could shift back toward the Germans. The investigations had to find answers quickly, and those answers had to enable construction to continue. What the investigators discovered was more complex than simple welding failures. Constance Tipper, a metallurgist from Cambridge University working with the British Ministry of War Transport, conducted systematic testing of steel samples from fractured Liberty ships. Her findings were definitive and troubling. The fractures didn't originate in the welds. The welds themselves, even those made by inexperienced workers, were generally sound. The problem was the steel itself, specifically how it behaved at different temperatures. Steel, Tipper demonstrated, has what's called a ductile to brittle transition temperature. Above this critical temperature, steel is ductile, meaning it can deform, bend, and absorb energy without fracturing. Below this temperature, the same steel becomes brittle, meaning it fractures suddenly with little or no deformation. The steel used in Liberty ships had a transition temperature that was too high. In the cold waters of the North Atlantic, where surface temperatures could drop below freezing and seawater temperatures hovered just above, the hull steel was operating in its brittle range. In a riveted ship, this might not matter. Riveted joints created what engineers call crack arresters, discontinuities that stopped crack propagation. In a welded ship with no such discontinuities, a crack that formed at a stress concentration point could race across the hull at thousands of feet per second. Brittle fracture, once initiated, was catastrophic and nearly instantaneous. The solution required both immediate and long-term responses. Immediately, shipyards added reinforcements around stress concentration points. Crack arrestor straps, riveted steel bands, were installed around hatch corners and at the ends of deck structures. These modifications broke up the continuous welded structure, creating interruption points that would stop crack propagation. The reinforcements worked. Fracture rates dropped dramatically. Liberty ships with the modifications continued serving throughout the war and beyond with few additional structural failures. Longer term, the Maritime Commission developed Victory ships, an improved design that incorporated lessons from the Liberty ship fractures. Victory ships used better steel, with lower ductile to brittle transition temperatures. Frame spacing was increased from 30 inches to 36 inches, making the hull less stiff and more able to flex under stress. Design details were refined to eliminate stress concentration points or reduce their severity. The Victory ships, built from 1944 onward, were faster, more capable, and structurally superior to Liberty ships, though they never matched the earlier vessels' production numbers because the crisis point of the tonnage battle had already passed. But the fracture crisis, serious as it was, ultimately validated rather than undermined the emergency program. The investigators had identified the problem correctly, implemented effective solutions quickly, and enabled production to continue. The program adapted, learned, and improved. The fractures generated fundamental advances in materials science, in understanding of brittle fracture mechanics, in design techniques for welded structures, and in quality control procedures. These advances influenced ship design for the next half-century. The Liberty ship's structural failures, terrible as they were for the crews who died, ultimately made maritime transportation safer by forcing the industry to understand and address issues that traditional construction methods had masked. The cultural impact of the Liberty ship program extended far beyond tonnage statistics and production records. The program became a symbol of American industrial might, of the democracy arsenal that Roosevelt had promised, of the capacity of free societies to mobilize resources and organize production on scales that totalitarian regimes couldn't match. German and Japanese intelligence services tracked American ship production with growing alarm. The numbers seemed impossible. How could a nation build nearly 3,000 identical ships in less than 4 years? How? Could shipyards that didn't exist in 1940 deliver 3 vessels per day by 1943? The answer was complex, involving technical innovation, managerial expertise, labor force mobilization, and a fundamental rethinking of what ship construction could be. But at the heart of it was the willingness to break with tradition, to try unproven methods, to trust inexperienced workers, and to accept that problems would emerge but could be solved if people were given the authority and resources to solve them. Thompson's jackbacker wasn't just a clever tool. It was an embodiment of the program's essential philosophy. The people doing the work know things that planners and designers don't, and organizations that harness that knowledge will outperform organizations that ignore it. The standardization enabled by Liberty ships had broader implications for American industry. Suppliers of components could invest in specialized tooling knowing they would produce hundreds or thousands of identical units. Workers could specialize in specific tasks, developing speed and skill through repetition. Manufacturing techniques developed for ship construction influenced post-war industrial production. The massive cranes, rolling mills, welding equipment, and fabrication facilities built for the emergency program became peacetime industrial infrastructure. The training programs that taught workers welding, fitting, and assembly skills created a skilled workforce that powered America's post-war industrial expansion. The program also demonstrated the potential of government-industry cooperation when properly structured. The Maritime Commission didn't micromanage shipyard operations. It set requirements, provided funding, established standards, and then let shipbuilders figure out how to meet those requirements. When yards proposed innovations, the Commission evaluated them on merit and adopted successful ones rapidly. When problems emerged, the Commission supported investigation and solution rather than assigning blame. The relationship wasn't perfect. Bureaucratic conflicts and procurement issues certainly occurred, but the overall structure enabled rather than impeded rapid production. Henry Kaiser became the public face of the program, and his contributions were genuine and significant. His background in large-scale construction projects gave him insights into prefabrication and modular assembly that traditional shipbuilders lacked. His willingness to hire and train inexperienced workers, including women and minorities, expanded the available labor pool when skilled workers were scarce. His emphasis on worker welfare, from healthcare to childcare to decent wages, reduced absenteeism and improved productivity. His talent for publicity kept the program in the public eye and maintained political support. But Kaiser didn't work alone. William Francis Gibbs and his firm Gibbs & Cox adapted the British Ocean-class design for American production and developed the modular construction techniques. Todd Shipyards and Bath Iron Works brought shipbuilding expertise. Thousands of suppliers provided materials and components. Hundreds of thousands of workers performed the actual construction. And workers like Garrie Thompson, anonymous assembly workers earning less than $1 per hour, solved problems that engineering departments had missed. This distributed innovation, this harnessing of insight from every level of the organization, was perhaps the program's most important lesson. Military organizations are inherently hierarchical, shipbuilding is traditionally conservative, and major industrial programs usually concentrate decision-making authority at the top. The Liberty Ship program succeeded partly because it inverted this model, because it recognized that the assembly worker wedging steel plates together knows things about plate alignment that the naval architect sitting in an office doesn't, because it created channels for that knowledge to flow upward and influence actual practice. The war created conditions that enabled this inversion. When survival is at stake, when torpedoes are sinking ships faster than you can build them, when the timeline from problem identification to solution implementation has to be measured in weeks rather than years, organizations become willing to try approaches they would reject in peacetime. The Maritime Commission couldn't afford to dismiss Thompson's jackbacker because it came from a worker rather than an engineer. 5,000 man-hours per ship was too valuable to ignore regardless of the source. In peacetime, institutional inertia would likely have prevented such innovations from being adopted quickly, if at all. Procurement regulations would require formal evaluation. Engineering departments would want to study the device, test it, document it, perhaps redesign it to fit their standards. By the time the approval process completed, if it ever completed, the problem might have been solved differently or simply accepted as unavoidable. The emergency conditions of wartime production compressed these timelines dramatically, enabling innovation to move from conception to widespread adoption in weeks rather than years. This raises an interesting question about the nature of institutional innovation. The Liberty Ship program succeeded because emergency conditions forced organizations to operate differently than they would in normal circumstances. But the problems the program solved, the inefficiencies it eliminated, the bottlenecks it cleared, those problems existed before the emergency. They just weren't addressed because peacetime institutions prioritize different values: stability over speed, proven methods over experimental ones, credentialed expertise over practical knowledge. The post-war period saw many Liberty Ship innovations forgotten or ignored. When the emergency ended, when the immediate crisis passed, institutions reverted to traditional practices. Shipbuilding slowed dramatically. The vast yards at Richmond and Portland closed. Workers dispersed to other industries or returned home. The techniques that had enabled 3 ships per day in 1943 were largely abandoned, and by the 1950s, ship construction had returned to something approximating pre-war methods, though with better steel and more sophisticated equipment. This pattern repeats throughout military history. The British Army in World War I had trench workshops where soldier-invented tools and weapons could be evaluated and rapidly produced. By the 1920s, these workshops were gone, and the Army had returned to centralized procurement. The German military in World War II encouraged unit-level modifications and had liaison officers documenting field improvements. Post-war, the Bundeswehr reverted to more hierarchical structures. The American military's response to improvised explosive devices in Iraq initially relied on unauthorized field modifications that soldiers welded together from scrap metal. Eventually, these became official programs with formal procurement processes, but only after years of resistance. The pattern suggests that institutions fundamentally distrust the kind of distributed innovation that Thompson's jackbacker represented. Hierarchical organizations run on standardization, on predictable procedures, on controlled change managed from the top down. This makes sense for many purposes. When you're coordinating millions of people across global supply chains, standardization is essential. When you're maintaining equipment for decades, formal engineering documentation is necessary. When you're ensuring safety, rigorous testing and approval processes are justified. But this same standardization creates blindness to opportunities that people at working level can see clearly. The assembly worker knows why 1,200 clips are wasteful, but the procurement system that orders clips in bulk lots of 50,000 doesn't incorporate that knowledge. The welder knows which joint configurations are difficult to execute in tight spaces, but the engineering drawings are produced by people who haven't tried welding in those spaces. The crane operator knows how material flows through the yard, but the layout was designed by people who don't operate cranes. Good organizations find ways to capture this knowledge, despite institutional barriers. The Maritime Commission's willingness to evaluate worker suggestions and adopt successful ones was unusual for its time and remains unusual today. Most large organizations have suggestion programs, but few actually implement suggestions rapidly or reward contributors meaningfully. The existence of a formal channel doesn't guarantee that knowledge actually flows or that good ideas get adopted. The Liberty Ship program worked because the emergency created conditions where ignoring good ideas had immediate, visible, fatal consequences. Ships were being sunk. Production had to accelerate. Everyone understood the stakes. In that context, Thompson's device saving 5,000 man-hours per ship wasn't just interesting, it was essential. Implementation wasn't optional. The question wasn't whether to adopt it, but how quickly it could be deployed across all yards. Contrast this with peacetime military procurement, where average development timelines for new equipment stretch to 15 or 20 years from initial requirement to fielding. The process involves requirements definition, competitive bidding, prototype development, testing, evaluation, redesign, more testing, limited production, operational testing, full production, and finally fielding to units. Each step has valid purposes. Each checkpoint exists for good reasons. But the cumulative effect is that the military fields equipment designed for problems identified 2 decades earlier, using technology that's often already obsolete by the time it reaches operational units. Modern conflicts in Iraq and Afghanistan generated similar dynamics to World War II's Liberty ships. Urgent needs emerged. Protection against improvised explosive devices, counter-drone systems, communications equipment that worked in urban terrain, all problems that couldn't wait 20 years for solutions. The result was another wave of unauthorized field modifications, followed eventually by formal programs to legitimize what soldiers had already built themselves. The MRAP, mine-resistant, ambush-protected vehicles, started as improvised up-armoring of existing trucks, before becoming a formal procurement program. Counter-IED jamming systems began as commercial electronics, modified by soldiers before official versions were developed and deployed. The lesson isn't that regulations are bad or that formal processes should be eliminated. Unauthorized modifications can be dangerous. They can create supply nightmares. They can introduce failures that kill people. Standards exist for good reasons. Testing procedures exist for good reasons. Engineering documentation exists for good reasons. The lesson is that the gap between what equipment does and what operators need will always exist, and creative people will always try to close that gap, regardless of regulations. The question for institutions is whether to suppress that creativity, harness it, or ignore it until it becomes impossible to overlook. The Liberty Ship program demonstrated that harnessing works better than suppressing or ignoring. Thompson wasn't punished for creating an unauthorized tool. He was celebrated. His device was evaluated quickly, adopted rapidly, and implemented across the program. Other workers saw that innovations were rewarded rather than punished, that solving problems was encouraged rather than suppressed, and they contributed their own improvements. The 3,000 worker suggestions the Maritime Commission received weren't just complaints or minor tweaks. They were substantial innovations that collectively saved $45 million and 31 million man-hours. $45 million in 1943 dollars translates to approximately $800 million in 2025 terms. 31 million man-hours represents 15,000 workers working full-time for an entire year. This wasn't marginal improvement. This was transformative innovation emerging from the workforce itself, not from engineering departments or research laboratories. The broader implication extends beyond shipbuilding or military procurement. Any large organization, whether military, industrial, or governmental, faces the same fundamental challenge: how to harness the knowledge of people doing the actual work while maintaining necessary standards and coordination. Organizations that solve this problem well will outperform organizations that don't. Organizations that create effective channels for knowledge to flow from working level to decision-making level will innovate faster, adapt more quickly, and solve problems more efficiently than organizations that rely solely on top-down expertise. Thompson's story illustrates what this looks like in practice. An assembly worker, earning 95 cents per hour, identifies a specific problem based on direct observation. He develops a solution using materials available in the shipyard. He builds a prototype on his own time. The device works. Word spreads through informal networks. Supervisors see the value and report it through formal channels. The organization evaluates the innovation quickly, recognizes its merit, and implements it across the program. Thompson receives recognition but not bureaucratic obstacles. The innovation saves massive amounts of time and resources. Other workers see that problem-solving is valued and contribute their own innovations. This cycle, repeated thousands of times across the Liberty ship program, was a critical factor in the program's success. The technical innovations, welding and modular prefabrication, were necessary but not sufficient. The managerial innovations, rapid evaluation and implementation of worker suggestions, were equally important. Together, they created a system that could build ships at rates previous generations would have considered impossible. By the end of the war, American shipyards had built 2,710 Liberty ships, the largest class of ships ever constructed to a single design. An additional 531 Victory ships had been completed by 1946. Beyond Liberty and Victory ships, emergency shipyards built tankers, troop transports, tank landing ships, and smaller vessels, contributing to a total wartime output that increased American shipbuilding capacity by nearly 1,200% compared to pre-war levels. The tonnage battle, the race between construction and destruction, ended decisively in Allied favor. U-boat sinkings peaked in 1942 and declined thereafter as Allied anti-submarine warfare improved and convoy tactics evolved. By 1943, new construction exceeded sinkings every month. By 1944, Allied merchant tonnage was actually increasing despite ongoing losses. The arithmetic of attrition that had threatened Britain's survival in 1941 reversed completely. Germany couldn't sink ships faster than America could build them, and that imbalance was ultimately as decisive as any battlefield victory. The ships carried armies to North Africa, Italy, France, and the Pacific Islands. They hauled fuel, ammunition, food, and equipment. They transported the jeeps, tanks, and artillery that equipped Allied forces. They moved the replacement aircraft that kept air forces operational. They delivered the raw materials that kept British and Soviet factories producing weapons. Every Allied offensive, every sustained operation, every advance against Axis forces depended on merchant shipping to maintain supply lines across oceans. Without Liberty ships, the Allied strategy of accumulating overwhelming material superiority and applying it through sustained operations would have been impossible. The human cost of merchant shipping was substantial. Merchant marine casualties during World War II included approximately 9,300 dead from various causes, including enemy action, marine accidents, and disease. The casualty rate for merchant mariners was higher than for any military service except the Marine Corps. Ships were torpedoed, bombed, shelled, and mined. Crew members died in explosions, fires, drownings, and exposure. Many merchant ships sailed without adequate defensive armament, making them vulnerable targets. The SS Stephen Hopkins, a Liberty ship, engaged in a gun battle with the German commerce raider Steer in September 1942, becoming the first American merchant ship to sink a German naval vessel. The Hopkins also sank in the engagement, with 15 survivors drifting for a month in a lifeboat before reaching Brazil. These losses underscore that Liberty ships weren't just industrial artifacts or economic statistics. They were operational vessels that sailed into war zones, crewed by civilians who volunteered for service that was often as dangerous as military combat. The ships that Thompson's jackbacker helped build faster didn't just exist as abstractions. They carried actual cargo to actual destinations, sailed through actual combat zones, and sometimes got people killed when they were lost. The urgency that drove the program, the pressure to build faster and cheaper, wasn't abstract either. Every day of delay was a day when ships at sea lacked replacement, when convoys sailed undermanned, when losses couldn't be replaced. Many were laid up immediately after the war, anchored in reserve fleets at Suisun Bay in California, the James River in Virginia, Beaumont in Texas, and other locations. The ships sat for years or decades, maintained in preservation status against possible future need. During the Korean War, many were reactivated and returned to service. Some were modified for specialized purposes: aviation, transport ships, repair vessels, storage hulks. Others were sold to foreign shipping companies and continued commercial service under various flags. A few were even converted to other purposes entirely, with at least one becoming a floating hotel. The scrapping of reserve fleet Liberty ships began in the 1960s and continued for decades. By the 1980s, most had been cut up for scrap metal, though a handful survived as museum ships or memorials. The SS John W. Brown, preserved in Baltimore, and the SS Jeremiah O'Brien, preserved in San Francisco, are both maintained in operational condition and occasionally make demonstration voyages. These surviving ships allow modern visitors to experience, at least partially, what the wartime vessels were like: the massive cargo holds, the antiquated steam engines, the cramped crew quarters, the utilitarian construction. Walking through a preserved Liberty ship provides perspective that statistics alone can't convey. The scale becomes tangible. The simplicity of design is evident in every detail, from the exposed pipes running along compartment overheads to the basic bunk arrangements in crew quarters. The evidence of welding is everywhere, seams and joints visible throughout the hull and superstructure. The cargo holds are vast, empty spaces, 5 separate compartments running the length of the ship, each capable of swallowing dozens of vehicles or thousands of tons of bulk cargo. Standing on deck, looking at the length of the vessel, the 41-foot beam becomes real in a way that numbers on a page don't capture. These ships were built in weeks, not months. They were constructed by workers who had never welded before, assembled from modules that travelled across the country by rail, powered by engines that were considered obsolete when installed. They were ugly, unglamorous, and absolutely essential. Without them, the Allied war effort collapses. With them, victory became inevitable, though not immediate, and not without terrible cost. Garrie Thompson's jackbacker, the device that eliminated 1,200 clips per ship and saved 5,000 man-hours, was a small part of this massive enterprise. Thompson himself remains largely anonymous. His name appears in a few historical accounts of shipyard innovations, but there's no monument, no museum exhibit, no public recognition of his contribution. This anonymity probably wouldn't have troubled him. He was solving a problem he saw every day, using skills he'd developed from experience, contributing to a war effort where everyone understood the stakes. The fact that his solution worked, that it saved time and resources, that it helped build ships faster, those were reward enough. But Thompson's story, and the thousands of similar stories from workers throughout the Liberty ship program, contain lessons that remain relevant. Innovation doesn't require credentials or formal expertise. It requires observation, understanding, and the willingness to try something different. The assembly worker who sees waste isn't less qualified to solve problems than the engineer who designed the original process. They just have different knowledge, and if the organization can harness both kinds of knowledge, top-down technical expertise and bottom-up practical understanding, it will outperform organizations that rely on only one. The challenge is creating systems that actually capture and implement this knowledge. Formal suggestion programs aren't enough if suggestions disappear into bureaucratic processes without evaluation or response. Management pronouncements about valuing worker input aren't enough if the actual experience of proposing changes is that nothing happens. What matters is the lived reality. When someone identifies a problem and proposes a solution, does the organization evaluate it quickly, implement it if it works, and recognize the contributor? Or does the suggestion vanish into procedures that may or may not eventually produce a response? The Liberty Ship program got this right, because the emergency conditions created accountability. Thompson's jackbacker saved 5,000 man-hours per ship. That savings was measurable, immediate, and significant. The organization couldn't afford to ignore it. Peacetime institutions face less pressure and often respond more slowly or not at all. The question is whether organizations can maintain the responsiveness that emergency creates without requiring actual emergencies to motivate change. Modern manufacturing has partially addressed this through concepts like continuous improvement, lean production, and worker empowerment. These approaches, often traced to Japanese manufacturing practices developed post-war, incorporate many principles the Liberty Ship program demonstrated during the war. Workers are encouraged to identify waste, propose improvements, and participate in problem-solving. The best implementations create cycles of observation, experimentation, and adaptation that continuously improve processes. The worst implementations treat continuous improvement as a slogan rather than a practice, creating suggestion systems that exist on paper but don't actually change how work gets done. The difference between effective and ineffective systems usually comes down to whether workers believe their contributions matter. If suggestions are evaluated quickly and implemented when they work, workers will continue contributing. If suggestions vanish into bureaucratic processes with no feedback or action, workers stop bothering. The Liberty Ship program worked because workers saw their contributions implemented rapidly and recognized publicly. The Maritime Commission tracked suggestions, calculated savings, and publicized successful innovations. Workers knew that problem-solving was valued, and they responded by solving problems. This creates a virtuous cycle. Organizations that effectively harness distributed knowledge perform better. Better performance creates more resources to invest in improvement. More improvement creates better performance. Organizations can enter this cycle at various points, by creating better channels for suggestion, by evaluating ideas more quickly, by implementing successful innovations more broadly, by recognizing contributors more visibly. Once the cycle begins, it can become self-reinforcing. The Liberty Ship program entered this cycle under emergency conditions that eliminated barriers to rapid change. The challenge for modern organizations is achieving similar responsiveness without requiring emergencies. Some succeed. Toyota's production system, for example, incorporates principles that resemble Liberty Ship program practices. Workers are expected to identify problems and stop production when issues emerge. Improvements are implemented rapidly. Knowledge flows both up and down the organizational hierarchy. Other organizations struggle despite similar intentions, often because the formal structure promotes improvement while the actual culture punishes deviation from standard procedures. The question ultimately comes down to organizational design and culture. Can you create institutions that combine the benefits of standardization, necessary for large-scale coordination, with the benefits of distributed innovation, necessary for continuous improvement? The Liberty Ship program suggests this combination is possible, but requires specific conditions. Clear objectives everyone understands, rapid evaluation of proposed changes, authority to implement improvements, recognition of contributors, and willingness to accept that the people doing the work know things that planners don't. These principles extend beyond manufacturing or shipbuilding. Any large organization, whether building ships, developing software, providing healthcare, or managing logistics, faces similar challenges. Frontline workers observe problems that management doesn't see. They develop practical solutions that formal processes overlook. If the organization can harness that knowledge, it will outperform competitors that can't. If it ignores or suppresses that knowledge, it will accumulate inefficiencies until crisis forces change or competition eliminates it. The Liberty Ship program's ultimate lesson isn't about welding technology or modular prefabrication, though those innovations were important. The lesson is about how organizations learn, adapt, and improve. The program succeeded because it created conditions where Thompson's jackbacker could move from concept to implementation in days rather than years, where worker suggestions could save millions of man-hours because someone actually evaluated and adopted them, where the barrier between identifying problems and solving them was minimal rather than insurmountable. Creating those conditions required emergency pressure in 1942. The question for the 21st century is whether similar responsiveness can be achieved without requiring emergencies, whether institutions can incorporate the lessons the Liberty Ship program demonstrated, whether organizations can combine stability with adaptation, standardization with innovation, top-down coordination with bottom-up problem-solving. The stakes may be different than they were in 1942. U-boats aren't sinking merchant ships. The survival of democracy doesn't depend on building 3 ships per day. But the fundamental challenge remains. How do large organizations harness the knowledge and creativity of everyone contributing to their work? The Liberty Ship program, for all its specific historical context and wartime conditions, offers a model that remains relevant. Listen to the people doing the work, evaluate their ideas quickly, implement what works, recognize contributors, create cycles where improvement becomes normal rather than exceptional. Thompson's jackbacker, a simple tool that looked like a cast iron femur with a bolt through it, wasn't just a clever device. It was proof that some of the most important innovations come from unexpected sources, that practical knowledge matters as much as formal expertise, that organizations wise enough to harness distributed intelligence will outperform those that don't. 83 years later, welders and shipbuilders still face problems with aligning plates for welding. Modern tools are more sophisticated, but the underlying challenge remains the same. Thompson's solution: eliminate wasteful temporary fasteners by using mechanical advantage to draw plates together, remains valid. The ships Thompson helped build faster, ships that carried armies across oceans and supplies across war zones, are almost all gone now, cut up for scrap or resting on the bottom of various seas. The yards where they were built have been redeveloped or demolished. Vanport, the city Kaiser built to house shipyard workers, was destroyed by flooding in 1948. The massive cranes that lifted prefabricated modules have been scrapped. The welding equipment has been replaced by newer technology. The workers have aged and died, taking with them direct memory of what it was like to build 3 ships per day, while submarines were sinking merchant vessels, and the survival of civilization hung in the balance. But the lessons remain accessible to anyone willing to study the history. The Liberty Ship program demonstrated what's possible when organizations combine clear objectives, distributed authority, rapid adaptation, and respect for practical knowledge. It showed that ordinary people, given responsibility and opportunity, can solve extraordinary problems. It proved that some of the most valuable innovations come from the people doing the work, not from the ones designing it. And it established that organizations wise enough to harness that knowledge will outperform competitors that don't. These lessons applied in 1942 when Thompson invented the jackbacker. They apply today when workers identify inefficiencies in manufacturing, healthcare, logistics, software development, or any other field. They'll apply tomorrow when new challenges emerge, requiring new solutions. The specific technologies change, the underlying principles don't. Listen to the people doing the work. They know things you don't. Give them authority to solve problems they observe. Evaluate their solutions quickly. Implement what works. Recognize contributors. Create cycles where innovation becomes normal. The Liberty ships themselves, ugly ducklings that won a war, serve as monuments to what's achievable when these principles are followed. 2,710 ships, built in less than 4 years, by workers most of whom had never built ships before, using technologies that skeptics said wouldn't work, at speeds experts said were impossible. Each ship represented hundreds of innovations, large and small, from Thompson's jack-backer to improvements in welding techniques to better material handling systems. Each innovation came from someone who saw a problem and fixed it. That's the essence of the story. Not the technology, not the scale, not even the remarkable production statistics, though all of those matter. The essence is that when Thompson saw 1,200 wasteful clips, he didn't accept waste as inevitable. He built a better solution. And the organization, pressed by emergency but also structured to recognize good ideas, adopted his solution and applied it broadly. That pattern, repeated thousands of times, built the ships that won the war. The next Thompson might be working in a factory, a hospital, an office, or a laboratory. They might be identifying waste, designing improvements, or solving problems that experts have accepted as unsolvable. The question is whether organizations will recognize and support them the way the Liberty Ship program recognized and supported the original. History suggests the answer matters. Organizations that do will thrive. Organizations that don't will struggle, wondering why innovation happens elsewhere while they follow procedures that no longer serve their purposes. 83 years after Thompson invented the jack-backer, the tool itself is probably lost, either scrapped as surplus equipment after the war or rusting in some forgotten shipyard storage area. But the principle it embodied, that workers who see problems can solve them if given opportunity and authority, remains as valid as ever. The challenge is creating organizations that recognize this truth and act on it, not just in emergencies, but as standard practice. The Liberty Ship program showed it's possible. The question is whether modern institutions can learn from that example before the next crisis forces them to. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.